Hello guys, you're welcome back to my channel, and in this video we are going to solve an example, not just one. We're going to solve a couple of examples. We're trying to classify these second order partial differential equations. Luckily for this first example, there are no first order terms, and even if there were, there wouldn't be we wouldn't be concerned about them because we are always interested in the second order terms. So if you guys really remember, the first thing we're going to do is to write the symmetric matrix out of this. That's going to be A11 is 1, A22 is going to be 2. Now A12 is going to be this entire thing divided by 2, okay? So that's going to be negative 3 over 2 and negative 3 over 2, okay? All right, so normally we are supposed to find the eigenvalues of this, but if you just have a 2 by 2 symmetric matrix, we already know that the product is given as A11 A22 minus A12 squared, okay? So you don't really have to go into solving for the eigenvalues because that is quite simple here. The sign is determined by this delta here, okay? So we already know what A11 is, so my delta is going to be A11 is 1, A22 is 2, minus, I'm going to have negative 3 over 2, all squared. And that's going to be 2 minus 9 over 4, and that is going to give us negative 1 out of 4. And this is less than 0. And when you have it to be less than 0, what happens if you have the product to be less than 0? It means that you have a hyperbolic PDE, right? Have a hyperbolic PDE. So if you have a hyperbolic PDE, it means that you have this equation here, looks like the wave equation. You can solve it as though you're solving the wave equation, okay? Yes. So another example, where is it? Yeah, you have y uxx plus xu yy equals 0. So here you're gonna have your a is going to be y x, and these are going to be zeros, right? Because you don't have any mixed derivatives in here. Actually, it's just a derivative of just one of the space variables. And what do you have here? You're gonna have your delta being equal to a1, which is y x, so I can call it just xy because you have a11 multiplying a22, so it's going to be xy minus 0, which is just going to be xy. So now looking at this is going to depend on the values of x and y's. So the sign of the the PDE, the sign that is going to determine whether you have a hyperbolic PDE, whether you have an elliptic or a parabolic, is going to depend on the values of x and y, okay? Yes. So in this case, I can show the regions where you're going to have elliptic PDE, the region where you're going to have a parabolic one, where you're going to have a hyperbolic one, okay? So when x or y is equal to 0, you're going to have delta being equal to 0. So whenever x or y is equal to 0, which are these points on these lines, okay? Let me call it this. Okay, that's going to give you a parabolic PDE. So when x or y is 0, or both of them are 0, okay? Yes. Also, if both of them have the same signs, that's if x and y are both positive, or if x and y are negatives, then you're going to have an elliptic one because it's going to give you a delta of positive right? So these quadrants are going to give you elliptic PD. Okay, so that is when x and y, and y have the same signs. So, and if they have opposite signs, that's going to be that quadrant, then that is going to be a hyperbolic one. Okay, yeah, so anytime you have the, your delta being a product of these space variables, then you're going to have different scenarios of the second order partial differential equations. Okay, yes, so these two were very simple. So now let's pick something not so challenging, but another example. It's not really challenging, but it's really simple as well, but it's going to be a bit different from what we done so far. So 2uyy plus 2uxz plus uzz equals 0. Okay, so now that we have something like this, our A is going to be a bit different. Okay, so your diagonals are going to be 3 because you have 3 spatial variables. You have x, y, and z. So the matrix is going to be a 3 by 3 matrix. Okay, so the diagonals are going to be 3, 2, and 1. So if you're thinking of how we got these diagonals, 3, that's the coefficient of uxx, 2, coefficient of uyy, and 1, which is the coefficient of uzz. Okay, so those are how we are referring to. And then these parts here are going to be 0 because, write this out as something like this, x, y, and z. Okay, so xx, that gives you 3. xy, you don't see any uxy, so it's just going to be zeros. Okay, uxy is supposed to be equal to uyx, but there is a uxz here, so xz here is supposed to be 2 divided by 2 because you're supposed to divide. It's a symmetric matrix. You're supposed to divide everything by 2 and then distribute over the entire matrix. So you're going to have 1 and then 1 here, and then uyz, there is no uyz, so that's also going to be 0, and that is your A. All right, yes. So with this, we have to solve for the eigenvalues because this is no more a 2 by 2 matrix, right? So we have to solve for so we have 3 minus lambda, 0, 1, 0, 2 minus lambda, 0, 1, 0, 1 minus lambda. This is what we have. And if you solve this, okay, you should realize that your lambdas, let's just do it. I want to pick this portion, plus, minus, plus, minus, plus. So I'm going to have 0, I'm going to have 2 minus lambda, okay, multiplying 3 minus lambda, 1, 1 minus lambda. Am I right? All right, so that's what we have, and that should be equal to 0. I didn't put 0 there. Yeah, so I'm gonna have 2 minus lambda, all multiplying 3 minus lambda, 1 minus lambda, minus 1 equals 0. Okay, so here you can see that lambda is already 2 because let me write this first. We have 2 minus lambda equals 0, lambda 1 equals 2, and then you have 3 minus lambda, 1 minus lambda, minus 1 equals 0. You're going to have 3 minus 3 lambda plus minus lambda plus lambda squared minus 1 equals 0. So you're going to have lambda squared minus 4 lambda plus 2 equals 0. Wait, am I right? Yeah, I guess I'm right. So this is gonna give us lambda 2 and 3 gonna be 2 plus or minus square root of 2, and you can see that all lambdas, lambda 1, lambda 2, lambda 3, are all greater than 0. Okay, and once you have the products, or you have all the eigenvalues being greater than 0, it means the product is also going to be positive. They have the same signs, so you're going to have a positive, delta, right? And that is an elliptic PDE. So we have an elliptic PDE. Okay. Yes. So let me give you some example for you to try just by yourself. Or an example, so you can try this by yourself. And that's going to be x squared uxx plus 2x uxy plus y squared uyy equals 0. Okay, so you can try this by yourself, and then you should get your, it's going to be very simple. I know you should be able to do it, so give it a try. And so see you in the next video, where we are going to start talking about the wave equation, solve the wave equation, and then move on to the other equations. That's where things get interesting. Okay, all right, see you.